Good evening, everyone. Welcome. My name is Julie Konzek. I'm a program manager in continuing education here, and it's my pleasure tonight to welcome you and to introduce our speaker. Professor Joe DalSanto has always had a deep love for astronomy and has enjoyed teaching it for over 20 years. Since joining COD in 2012, he has authored an astronomy textbook, 2 lab manuals, chaired the Earth Science Department since 2018, and recently led the development of our virtual reality and an immersive visualization lab. But his greatest joy and satisfaction has always been sharing astronomy with his students, both in the classroom and in the public. Please welcome Professor DalSanto.
Thank you, Julie, and good evening, everyone. Always nice to be back here. See a lot of familiar faces, so nice to have you back, and a lot of new faces as well. Thank you for joining us tonight. As you can see, I've prepared, I think, a good topic for us tonight. I call it The View from Earth, to imply what we have seen and learned about this vast universe in the last 400 years. So my work is cut out for me. There's no way I could possibly cover most of the discoveries we've made, but I do want to share a sequence of them, I think you'll see, to show how our knowledge has built over those years. And I want to emphasize, you'll hear me say this from time to time, that there were times we did not know things, and then obviously we discovered them. And that carries on today. There's many things we don't know yet. There's many things we maybe have discovered. Some of you have asked me about the latest from the James Webb Telescope. And we saw this, and we think we found that. That's great. Now we have to evaluate that and see where that fits into our knowledge. Maybe it changes our knowledge. That's why we do science. So let's get started. We're going to go back in time and begin with just a little bit of context to get us started. If you were to go back a couple thousand years even, the ancient Greeks came up with the very first model of the universe that was reasonably scientific. Prior to that, as you can see here, ancient cultures had some ideas, but they really weren't doing science yet. Sure, they observed patterns in the sky, they noticed the moon going through its phases, they developed calendars, things of that nature. They could even predict when the eclipses would come. Unfortunately, we didn't get to see one here in Chicago today, but there was, maybe you know, a solar eclipse today. But again, these ancient Greeks developed the first model, we'd call it, called the geocentric model, Earth-centered model. And you might know the name Claudius Ptolemy. Claudius Ptolemy is the one who took the information from a number of different Greek astronomers and brought it together and built this particular model. And I got to say, at the time, it worked pretty well. So it was accepted. People adopted it, and very few were qualified to challenge it, really. And so it lasted a very long time. Over time, though, some would look at it and say, well, something's not quite right with that. But it really didn't challenge the prevailing theory, if you will, of the time for quite a long time. Here you see an example of that. He put the Earth at the center because it sure feels that way, doesn't it? In our everyday experience, it sure looks that way. If you look up at the sun, the moon, the stars, they sure look like they're going around the Earth. And so he developed that into a theory that held for, as you can see here, 1,500 years. Quite a long time. People didn't give a lot of thought to it. But eventually, some did. And that takes us to our next step here. You might know the name Nicholas Copernicus. In the early 1500s, he began to put together a little different model, in fact, a very different model, a sun-centered or heliocentric model of the universe. And he knew that this would be a very difficult thing to sell. In other words, people were going to even ridicule him. How can you think this Earth is moving? We don't feel it. What evidence do you have? So frankly, Copernicus was a little slow to actually go ahead and publish that. His friends had to urge him to do that. But in 1543, a very famous book was published by him before he died. In the next few decades, another important name appeared on the astronomical scene here. Tycho Brahe was a Danish nobleman who made very extensive, very accurate, very systematic measurements of stars, planets, the moon in the sky. He did what we would today probably call collect data. He wasn't just coming up with a new idea, but he was out very meticulously measuring the motions of objects in the sky. That proved very important, and you'll hear this as a recurring theme tonight. Science often starts with collecting of data, observations, measurements, and then, of course, we want to make sense of those. So Brahe puts together these observations. He actually tried his hand at a new model, but it didn't work all that much better, so it didn't go too far. But as we now move forward even a few more decades to right around the year 1600 or so, the man you see on the lower right here, Johannes Kepler, now kind of steps forward. He's a mathematician, but he's very interested in how the heavens work. And he hears that Tycho Brahe has made all these measurements, and he's eager to get his hands on them. Because again, by now, this new sun-centered or heliocentric model has been published, and some are reviewing it. And he would love to be able to see this data and see if it can help him understand better that new model. And he is able to determine 3 laws of motion for planets. The first 2 came fairly straightforward, but the third one took a while. You see them illustrated here. Simply put, up until this time, people still thought the planets went around the sun in circles. And Kepler figured out that couldn't work mathematically. What he did find, you see there in the blue, is that the planets, as they orbit the sun, they do get a little farther away and a little closer, and they actually changed speed. That was quite a revolutionary idea. Planets can speed up and slow down? Yeah, that's exactly what they do. Today we know a lot more, obviously, as to why that's the case. And then right below that, you can see a very simple equation, p squared equals 8 to the third. My students know all about it. They've been learning about that recently. He found a mathematical law that relates the period that the planet takes to orbit with its average distance from the sun. In other words, the farther out the planet is, clearly the longer it takes it to orbit. But there's a specific mathematical relationship for that. So these were big steps to our beginning to understand how this new sun-centered heliocentric model would work. At about the same time, Galileo steps forward as well. Probably heard that name before. And here our view of the universe is going to change again dramatically. He's firmly convinced that this sun-centered model is working, and he's not only made some writings already, but by 1609, he's the first one to take a telescope and look up at the heavens with it. We don't necessarily think he invented the telescope, but he was the first one to really use it significantly in astronomy. And I got to tell you, we sometimes envy him a little bit because he saw things no one had ever seen before. He saw moons going around Jupiter. He saw phases of Venus, which I'll get to here in just a second. But this was more information that he could use to try to make sense of our universe. You can see here, too, he tried to share that with others. And you might know part of the story that some were a little hesitant, a little bit reluctant even, to accept what he was trying to show them and teach them. But we like to say the evidence was there. The evidence was there, and it just was a matter of people needing to accept it. Okay, so let's take a look at what I was just describing. You can see here some of his early drawings. We'll start down in the lower left. One of his early drawings of the moons orbiting Jupiter. And again, some of my students have been reproducing this with simple binoculars even. You can see these moons. This was significant because it was clear evidence that there were bodies out in space that did not orbit the Earth. That old Earth-centered model dictated that everything orbited the Earth. Well, here was clear evidence that there were 4 moons going around Jupiter that did not orbit the Earth. Might seem simple to you and I today, but it was a significant observation. In the upper left, you can see a sketch of his drawings showing how Venus appears to go through phases like our moon. Now, that might just seem an interesting observation, but it was crucial to proving once and for all that the old Earth-centered model could not be true, that the sun-centered model had to be true. Look at the larger diagram here. Let's go to the left. You can see that the model with the Earth in the center, the sun is out actually farther than Venus. That model said that the planets like Venus would move around in what they used to call epicycles. If you look closely at that diagram, you'll notice that Venus would always appear as a crescent phase. Can you see that there? But if you look in the right-hand model, now the sun-centered model, correct, of course, sun's in the center, we are out farther from the sun than Venus, and I think you can clearly see, being on a closer orbit to the sun, Venus is going to have a shorter distance to travel, and it's going to move faster than the Earth. It's going to go through all the phases that our moon does. That could not be possible if the Earth was the center. So these two facts, especially that second one, really finally did away with that Earth-centered model. Astronomers at this point in time, when they began to see that, realized that here was observational proof. Of course, that's a recurring theme, not only in astronomy, but really in all of science. When we make observations and they're solid and we're confident in them and they've been reproduced, then we accept them. They tell us something new about the universe. Our view of the universe changes. Let's go forward a few more decades now into the mid to late 1600s. Very famous scientist Isaac Newton now steps up, and he is experimenting and learning more about things like motion. He develops 3 laws of motion that we still can use today. And of course, the famous law of gravity. There you see it in our diagram. This was a huge breakthrough to be able to now accurately describe how gravity works. In other words, sure, people could drop things and say, well, sure, there's gravity, but Newton's able to develop an equation that you see here that we can still use today. The force of gravity is proportional, as you can see there, to M1 and M2. Those are the 2 bodies that you might be interested in, whether it's a planet and a moon or any 2 objects out in space, divided by the distance between them squared. And there's a gravitational constant there, g, as well. So the point is, here was another improvement in our understanding of how bodies moved. Prior to that, it was kind of like people would wonder, why does the Earth go around the sun? Why does the moon go around the Earth? Well, this is why. There is this force he postulated, and this equation described how it works. So we like to say that he went beyond describing what they did and began to explain why they did it. And that's often a big goal in science. It is often a first step to go out and observe and describe, but sooner or later, doesn't that question always seem to come up? Why is it doing that? How is it doing that? This equation was a big step forward that Newton gave to us. As we continue to move on now into the late 1700s, early 1800s, the gentleman you see at the upper left there, William Herschel, is a very well-known astronomer. He started out as an amateur astronomer, something near and dear to my heart, and I'll bet many of yours. He'd go out and observe the heavens for the love of it. He wasn't any type of professional astronomer. He built his own first telescope, which, by the way, helped him discover the planet Uranus. So that got him noticed, got him some attention. He was brought before the King of England. You can see him out in the garden there with his sister assisting him looking through the telescope. But Herschel was so curious about what he called the construction of the heavens that he would go out essentially every clear night. He began to observe numerous small, faint, fuzzy objects in the sky. Today we would call them nebulae, okay? And he began to catalog them. That's often something that we do in many sciences, don't we? We collect information, we want to organize it and catalog it. And by the early 1800s there, he had published his catalog of star clusters and nebulae. So that was a good first step forward. Prior to that, most astronomers, they didn't have as big a telescope as he had. They couldn't see many of these, so they would focus their attention more on the solar system, the sun, the moon, the planets. Well, Herschel, I like to say, was really probably the first primary individual to push beyond the solar system. What else is out there beyond our, solar system? So he'd take some big steps. You can see then to his lower right there, his son John Herschel decided to pick up his father's work where he had left off. And by the 1830s, he took it upon himself now to travel to the southern hemisphere. His father, William, had done his observing from England, and he could see a fair amount of the sky, but he couldn't see anything from the southern hemisphere. Well, you got to give John Herschel some credit, too. He packed up a wife and several children and his father's new large telescope, sailed to the Cape of Good Hope, South Africa, set it all up, spent several years there observing the southern sky, also cataloging for the first time all the objects he could find. Those were added to his father's original catalog and eventually became what we today still call the New General Catalog of Non-Stellar Objects. So this was very painstaking, tedious work to go out night after night and visually observe. But these two really laid a foundation. They provided to all other astronomers what objects were out there, what did they look like, where were they in the sky, so that others could later follow them up and study them. As we move into the early 1800s, astronomers had many questions about these objects that were being found. But one of the first main questions, as you can see here, how far are the stars? Why was that so important? Well, think about it. If you look up in the night sky and you see stars, you might think, well, what are they? Today, of course, we know, but back then, we had some ideas. We thought maybe they were like our sun. But the point is, we couldn't get too far with understanding the stars until we knew how far away they are. How do you figure out how far away they are? Here you see a geometrical method that was adopted. As Earth orbits the sun, you can see in our diagram here behind me, nearby stars would appear to be seen from a slightly different perspective than the more distant ones. I want to try something with you that I always ask my students to do. Hold your finger up close to your nose and open and close each eye. I love seeing the audience look funny, but no, I'll do it with you. You see your finger shifting back and forth? But if you do the same thing and look out into the distance, things don't shift back and forth. Why is that? Because your finger's close. Each eye is seeing it at a little different angle. The technical name for that, as you can see, is the parallax angle. So the point is, astronomers correctly surmised that, well, if we could find some nearby stars and we observe them as Earth is on one side of its orbit, perhaps let's say January, and then we move around our orbit, and 6 months later, in June or July, we're going to observe that same star, we should see it make a little shift. And it was an exceedingly tiny shift, make no mistake, and thus it took quite some time to accomplish it. You can see it was first done here in 1838 by a man named Bessel. The amount of the shift, as you see in our diagram, can allow us to find the distance. We measure that angle, that tiny little shift in the sky. We know the baseline of Earth's orbit, and we can essentially construct a giant triangle and find the distance geometrically. This was a big breakthrough, because now that we knew the distance of those points of light in the sky, we could get a sense of, well, if they appear this bright to us, how much light must they actually be emitting? What we now call luminosity. So this was a big step forward by the mid-1800s to finally know how far away they were. And boy, were we shocked when we learned they were many light years away. Maybe you've heard that term. Maybe you know a light year is about 6 trillion miles. So you can do the math. 11 times 6 trillion miles. That's one of the closest stars. So we began to get a sense of how far away they were, and thus how relatively small our solar system was. Our view of the universe changed dramatically, didn't it? The next big step was to try to understand more about the stars. Well, if we know how far away they are, could we start to learn perhaps how massive they are, maybe how hot they are? What are they made out of? All these questions are natural for us to ask. Astronomers again began to employ a very novel method to try to figure those things out. They would observe what are called binary stars. Many of you are familiar with those. You can see an animation here showing how two stars would essentially orbit around each other, very much like a planet like Earth orbits the sun. But these are more equal in relative mass, generally speaking. Okay, so how would this work? Well, here we've, of course, dramatically sped up the animation, but astronomers would very tediously and very painstakingly go out, look through the large telescopes you see here, and plot carefully the positions of those stars over many years, in many cases, as they would slowly, gradually orbit around each other. This was crucial because a method began to be developed that if we could measure the period of the orbit, and if we could now measure the distance, the average distance between the stars, we could calculate their masses. And that turned out to be such a crucial piece of information, such a crucial fact to understanding the stars. Once we understood their luminosities, then their masses, now astronomers could begin to essentially build models of them. Well, if they're giving off this much light and they have this much mass, they have to be at this temperature. Then we began to try to think about, well, how do they make all that energy? And that led to further advances. So the point is, the work done in the late 1800s into the early 1900s, where astronomers would carefully observe and measure these binary star orbits that sometimes took decades for them to track these motions. Again, very tedious work, but it was laying a foundation to help us understand the masses of the stars. This is still a foundation for us today that we've built upon. Sure, we have newer, higher tech methods, but here's where it began. So the stars now gradually began changing in our view from, I call them points of light in the sky, to actual objects we understood. How big were they? How massive were they? How far away were they? How hot were they? My students have been just calculating some of these things in class as well. So this was a big step forward to understanding much better what the stars were. So I mentioned just briefly there's several of the things that we wanted to learn, and one of them was composition. Well, in the late 1800s, several astronomers began to explore how to do that using what we now call spectroscopy. You take a spectroscope as a device that takes the light from a bright star, breaks it into a rainbow. The early ones used prisms of light. Maybe you've seen that. Newer ones used other means. But very interesting, you can see two diagrams here in the upper left showing what they saw. Often, if we would take a star's light and break it into this spectrum, we'd see the bottom of the two. There we'd see basically a rainbow of colors. But interestingly, we began to notice these dark lines. So this was a puzzle at first. Other objects they would turn the telescope towards and break the light into a spectrum. They looked like these nebulae we were mentioning. These instead showed a spectrum you see at the top here where there was very few of the bright lines showing. So how did we figure out what this was all about? Turns out, by going back to the laboratory, taking various containers of gas and heating them up, astronomers could reproduce what they saw. And so at the top there, you see an example of the emission line spectrum of an element like hydrogen. We heat this up in the laboratory, we look at the light, we see these lines. We already know it's hydrogen from some other analysis. We see the same thing in the light from a star. What would you conclude? The star has hydrogen in it. Meanwhile, the bottom spectra we began to interpret as something a little different. Maybe the star is giving off a lot of different wavelengths of light, but maybe that light is passing through cool gas, not very hot gas like normally is in a star. Well, now the cool gas will absorb some of the wavelengths of the light coming from the star, and we see the dark lines. So do you see how this became a powerful tool for us to learn more about the stars? If we looked at the star spectrum and we saw either the bright lines or the dark lines, we could go back to our laboratory and compare that and identify the elements that were in the stars. We began to learn about their composition. Spectroscopy also began to help us understand the temperatures of stars. You can see on the right there, it's kind of in black and white, but a number of different spectra. And at first, all they could do were take those spectra of various stars and try to make some sense out of them, some order out of them. It's very interesting. This was about the time when women began to be invited to assist the distinguished male astronomers. They did some very important work. And they were able to begin to find patterns that the astronomers could then look at and go, oh, if we sort them in this particular order, this would be a range of temperatures. And to this day, again, we've built on this work. Notice here how these are labeled. If you can read that, they're behind me. At the top, the spectrum of what we now call an O-class star, then a B-class star, an A-class star. The O-class stars are the hottest. And if you go all the way down to the bottom, the M-class stars are the coolest. So by analyzing the light of the stars, we began to learn more about their temperatures, that all stars were not the same temperature. Some were quite a bit hotter, others quite a bit cooler. So now you could see we're adding to our knowledge, aren't we? We learned about their masses, their distances. Now we're learning about their temperatures and their compositions. Again, our view of the universe continued to change here in the late 19th century. Well, by this point in time, this question was beginning to be answered, but there was still more to be learned. Again, you see there kind of in the center a number of visual drawings of some of these beautiful objects. Astronomers could describe their appearance, but again, we wanted to know more about what they were. When we'd point the telescope at the object and take the spectrum, we'd get various results as we just described. Some appeared to be very hot gas. Others appeared to be having the spectrum of stars. Now, of course, simply looking through the telescope, we could sometimes make a good guess at that, couldn't we? Look to the upper right there, you see a cluster of stars. You wouldn't mistake it necessarily for a cloud of material. But other times you'd look at an object like in the lower left there and you'd say, well, that sure looks like it's kind of a cloud of material surrounding a central star. So it became evident that there were at least two different types of these nebulae. Let's start with the one on the lower left there, the small round one. Today we call this a planetary nebula. I always say it's not a very good name for it. It has nothing to do with planets. But to the early observers, it looked like a little round planet in the telescope. And today we can, of course, take a much clearer image of it. Turns out that after much work, we determined that what was happening here was that small little blue central star had expelled its outer layers. And that material now is expanding outward, drifting outward. That small central blue star there you see was what used to be the very center or core of the star. It's very hot. And very hot objects, we learned, give off powerful radiation. That radiation essentially would light up that other material that had been expelled. So gradually we began to learn this is what happens at the end of a star's life. Most go through a process where they expel their outer layers, and all that's left is that small central core. Let's shift over to the lower right there. You see a beautiful picture of a large red cloud kind of glowing there. It's much more irregular in shape, isn't it? And one of the clues to its characteristics is that there's quite a few stars there, isn't there? Notice just to the right of the red glow there, you see a cluster of stars. We began to call these clouds emission nebulae because they're emitting light on their own, essentially, that red glow you see there. What's happening here? Turned out that these were huge clouds of gas that stars were forming from. That's why you see quite a few stars there. And that's why you still see the glow of the material from which they formed. That red glow, by the way, turned out to be hydrogen gas. We now know stars are primarily made of hydrogen gas. So essentially, we began to view these. We like to use this term today, stellar birthplace. This is where stars form. They don't form in isolation. They form by the hundreds, the thousands many times, and form star clusters from these nebulae. So can you see how, again, our view of the universe is changing here as we begin to understand better what we're seeing? At first, we could draw them, we could describe them, but now we understood better what we were seeing. It really began to change our understanding. About this time as well, a new powerful technology became available. They called it photography. Maybe you remember that term, right? Well, here's where we would step away so much from just drawing things we looked at visually in the eyepiece of a telescope to taking the first photographs, the first images, we'd call them today. And this brought many advantages. Number one, we could take a time exposure. We could take a camera and allow it to take an exposure much longer than we can do so with our eyes. With our eyes, we simply look at something, we get a certain impression, our eye gathers a certain amount of light. It's kind of what we'd say, well, that's what I see, right? But a camera can take a time exposure. The faint light from these objects could build up, accumulate. And you can see the difference there from the top left to the upper right, the dramatic view of what we now know as the Orion Nebula in the eyepiece compared to what a photograph shows us. Below it is a famous galaxy. Many of you recognize the famous Whirlpool galaxy there. And so again, you see a dramatic difference between a drawing of it and a photograph of it. So long exposure photographs dramatically brightened the objects, but they also allowed us to see objects that were so faint the human eye could not see them. And that has only grown down to our day. The other thing, of course, that occurred was our images of these objects became less subjective. In other words, if you and I both look through a telescope, we may see things a little differently. Our eyes may not be equal. I know mine aren't as good as they used to be years ago. And so it became more objective to take an image of it. That then could not only be studied indoors at your convenience, it could be shared with others. They could also take images and we could compare them as well. So this was a significant step forward in astronomy to be able to take these images, these time exposures, and allow us to study these objects in much greater detail. Well, if I haven't said so already, you can probably guess as time has gone on, telescopes were getting bigger and better all the time. You saw one image earlier of a great big long refracting telescope that were used. But by the end of the 19th century, those had pretty much reached their limit. The largest one built right up here in Wisconsin at Yerkes Observatory was pretty much going to fill this auditorium, okay? So astronomers knew that they had kind of reached the limit with the older style of refracting telescopes, and they moved on to the reflecting telescopes. Here was one of the first big reflecting telescopes installed on Mount Wilson in California in 1908, 60-inch diameter mirror. For the time, that was a big telescope, one of the biggest. And you can see here, housed in its dome, several different astronomers working to operate it. The size of the telescope was very important. It gathered more light, made the images brighter, allowed us to see fainter objects, which generally meant more distant objects. So now our reach of how far can we see it out into space is growing and growing as the telescopes are getting bigger. So make no mistake, telescope size was very important to improve our view of the universe. In the early 20th century, two astronomers busily at work analyzing all the information I've just described both came to a very interesting way to display that information. And again, some of my students have just begun to learn about this diagram. Rather than tediously analyzing each star individually, mathematically, they found a way to do so graphically. What did they do? Well, let's have a look at our diagram here. First of all, we're plotting temperature on one scale, horizontal, and luminosity of the stars vertically. Now, there's two things I'd like you to take note of here. Notice temperature is plotted maybe opposite of what we normally do. Normally, we make a plot and things increase to the right, don't they? But notice that we are now in our diagram increasing the temperature to the left. Our luminosity scale, if you look closely, is an exponential scale. It doesn't increase just 1, 2, 3, 4, 5 times. It's powers of 10. 10 to the first, 10 to the second, 10 to the third. So in other words, we've compressed the scale, especially vertically, so that we can plot these out. That in itself told us that there was a tremendous range of luminosity, isn't there? In other words, if you picked out a star here with a luminosity of 1, which, by the way, just indicates that's the luminosity of the sun. We use the sun as our standard there. There are stars with luminosities of 100, 10,000, even 1,000,000 times the sun. That's pretty mind-boggling, isn't it? How can a star give off so much energy? Well, we can at least plot it. And when we did plot it, you can see that most of the stars lay along this diagonal line we now call the main sequence of stars. And again, my students have just been learning a little bit about why is that the case? Why do most of them lay along that? First of all, you'd look at that and you'd say, well, it becomes pretty clear, of course, that if the star is hotter to the left, it's higher luminosity, isn't it? It's giving off more light. It kind of makes sense. If you had an object that the hotter it got, it would glow with more light, but this is a much more extreme case of that. Eventually, in the early 20th century, we began to learn the reason why that was the case with stars. Today, we know the reason. It has to do with nuclear fusion within stars. Stars in their cores are so hot, so dense, that atoms fuse together and release enormous amounts of energy, nuclear energy. This began to help us understand, how did the stars make so much energy? How can we see them at such great distances? This diagram became a powerful tool for astronomers to understand that. You can see there's some stars to the upper right, the giants and supergiants. There's some to the lower left, the white dwarfs. What were those all about? Well, again, further analysis led us to understand why there were these other groups. Turns out these were older stars. They had evolved past that main sequence stage. They were no longer fusing the hydrogen to helium in their cores. They had dramatically changed, moved on to other energy sources. I won't go into detail right now. And for most all of them, they would first expand into a much larger size. You can probably guess if the star is larger, has more surface area, more light is emitted. So you can see how they moved to the upper right, because number one, they are emitting more light. But why to the right? Well, as they would expand larger, the surface reduced in temperature. They would spend some time in that particular stage producing energy with other means. But eventually, do you remember the diagram we saw earlier of a star that expelled its outer layers? Yeah, what we're seeing now is that once they expel their outer layers, what's left? A very small, very hot, dense little white dwarf star. So where do we plot small and hot? Down here in the lower left. How do we know that? Well, hot, of course, is to the left, but small is down to the bottom because it does not have a very large enough size to give off a lot of light. So can you see how the diagram gives us a deeper understanding of stars? Not only does it plot their properties today, but basically this diagram allows us to also trace what we like to call the life cycles of stars, how they evolve over time, how they change. Stars don't last forever. They can't possibly last forever. They form, they emit energy for long periods of time, but sooner or later, they run out of fuel and they change. And it's quite a story to understand many of those details. So we began to understand them, and here I'll just illustrate what I've been describing. I'll keep it simple and break it into two different bins here, so to speak. Number one, the lower mass stars, like our sun, and smaller, those are not going to have as much mass. Therefore, their gravity is not going to be as strong. Therefore, they will find a stable state where their core is hot enough to produce energy to balance the gravity. Okay, so they balance out. Our sun is a very stable star. Deep in its core, it's making energy, but the gravity is containing that. But again, sooner or later, that fuel is going to run out. And here's where it goes through changes. I can't go into all the details tonight, but they're going to expand, as you can kind of see in the upper right, and expel those outer layers out into space. Remember, we saw the picture of the planetary nebula. Remember that? So there's your example there in the upper right of the star first expanding, then emitting its outer layers. What's left? Those white dwarf stars that we just saw as well. How about higher mass stars? Well, because they are more massive, gravity is stronger. It compresses them more greatly. That core gets hotter. It must find a way to make more energy to balance that stronger gravity. Well, to make more energy, it has to use up its fuel faster. It's a little bit like if you want to go faster, you got to press on that gas pedal, don't you? And use up more gas. So our high mass stars are going to use their fuel more quickly. They're going to live much shorter lives than the low mass stars. The low mass stars, if I didn't mention, can often live for billions of years. That's 9 zeros. High mass stars, they may only live for some millions of years, tens of millions of years. So that's still long to you and I, but it's much shorter. They're using up that fuel faster. Again, I can't go into all the detail, but when they expand, they become unstable. And as you can see here, they don't just eject their outer layers, they explode violently. And these are the supernovae. Maybe you've heard that term before. Those supernovae create many of the heavy elements that you and I are made out of. Because all that material gets thrown out into space. New stars are going to form from that. Those new stars are going to form planets. And on at least one of those, here we are, right? So can you see how the HR diagram helps us understand the stellar life cycles? It's not just a matter of a snapshot of today. Yes, it gives us that. But we can trace the life cycle of stars of various masses. So the 19th century was a great time for stellar astronomy, but as we moved into the 20th century, people began to wonder if there was anything beyond our Milky Way galaxy. Let's start in the upper left there with this image you see. If you look really closely, this is a close-up view of what's known as a globular star cluster because it's shaped kind of like a globe. Look closely, you see a few of the stars kind of blinking just a little bit. Do you see that? A little bit of a change there? This was something that was very subtle, but it caught people's attention. Okay, I'll come back to that in just a minute. As I mentioned here, an astronomer named Harlow Shapley noticed something very interesting in the early 1920s about the distribution of these objects. You think, well, if I look out into space, I should pretty much see them all direction, right? But interestingly, he did not. And it wasn't just him. It was correct. And he began to think about that. He was trying to embark on a project to figure out how big our Milky Way galaxy was and where we were in it. Up till then, people just pretty much assumed we were in the center. Because if you stand outside at night and look at the Milky Way galaxy under a dark sky, it looks reasonably uniform in brightness, and you pretty much feel you might be in the middle. Well, Shapley embarked on a project that turned out to dramatically change our view of the universe. How did he do this? He went back to these clusters, and he devised a method to measure the pulsations of those stars, and it turned out that the length of time it took for the star to get brighter and dimmer and brighter and dimmer brighter and dimmer, that was directly related to the luminosity of the star. In other words, if he said, well, if the star takes 10 days to go through a cycle of bright and dimming, it is giving off this much light, maybe 10 times the sun. But if it takes 50 days, maybe it's giving off this much light. Pick a number, 50 times the sun. Do you see the key here? He could look at the period of variation, learn the luminosity, and earlier we learned that, well, if you know the luminosity of the star, you can gauge its distance. So he had a way to measure the distances to these clusters. And look at this plot I've kind of recreated. There's the sun over on the left, and look at all the little green dots. Those are the clusters. Does it look like to you we're in the middle? Not even close, is it? We're well off to one side, aren't we? And so Shapley realized, well, we're not at the center of all of those clusters. Where do you think it would be more likely that those clusters were centered on? Yeah, the center or the middle of the Milky Way. So it became apparent we were not at the center of the Milky Way galaxy, even though it looked that way. The center of the clusters was the center of the galaxy. We were 2/3 of the way out. So talk about a change in our view of the universe. It was a major shift in our perception, not so much less really than when we shifted the Earth out of the center of the solar system, out beyond the sun, right? Now we're shifting ourselves out of the middle of the Milky Way, way out beyond the center. So this, again, was a dramatic change in our understanding. Here tells what we now understand is the case. We have our Milky Way galaxy, that huge central region, but look where the sun is, way over to the right. About 8 kiloparsecs, that turns out to about 27,000 light years for those that are more familiar with that unit. You can see some of the other features here. By the way, do you notice the globular clusters there, those fuzzy little plink things all orbiting around the center? And now you understand why Shapley could look at that and say, yeah, we're not in the center of those, are we? We're off to the side. So a rather ingenious way of him to determine that and help us understand where we really were in relation to the Milky Way galaxy. By the 1920s, another well-known astronomer was hard at work. Here's Edwin Hubble. Ended up having a telescope named after him. He was interested to look out even beyond those globular clusters because he suspected that many of the faint little fuzzy objects way out in space might be other galaxies. Many astronomers at the time thought, no, that's probably not true. The Milky Way is the Milky Way, and these are smaller objects inside the Milky Way. How could you tell the difference? If this was class, I'd pause and make one of you answer, but it's not class. So you would need to know the distances, wouldn't you? Let's measure how far away they are. How do you find the distance of some faint little fuzzy object in the sky? Well, Hubble had a plan. He used a method very similar to what we just described back here, Harlow Shapley used. He knew that there were variable stars whose period of pulsation were related to their luminosity. And so you can see a graph here in the center. Notice that red diagonal line. These special stars were called Cepheid variable stars. And again, as I described earlier, notice the period of their variation is related to their luminosity. So Hubble had a greater challenge on his hands. Harlow Shapley could spot these in the nearby, relatively speaking, clusters. But if Hubble was correct, and these were other galaxies, he suspected they were quite a bit more distant, and he knew it would be very difficult to see an individual star in them. Well, look at that picture to the upper right. It's a famous picture that he took, and on a couple spots there, he's noted a little N, okay? But notice in the upper right, it says VAR, variable, and he puts an exclamation mark as he's all excited. I found one. I found one of those stars that's doing this. It was pretty much at the limit of the available technology of the time for him to detect that, but he's able to watch it getting brighter and dimmer and brighter and dimmer. That told him its period. He used that to find the luminosity. That gave him the distance. What was the distance? Well, although he was off a little bit on his first few calculations, he corrected that, and eventually we became to realize these other systems were not thousands of light years away, they were millions of light years away. The one you see here is the famous Andromeda galaxy. It's only a few million away, but over time, Hubble began to measure a few more and a few more and a few more. These objects were millions of light years away. So talk about a change in our view of the universe. Here's a big one. Here's a big one, okay? This is in the 1920s that Hubble establishes the discovery of other galaxies that we now know about today. Well, Hubble's not done yet. He's got another idea. He says, let me go ahead and not only measure the distances to these galaxies, several millions of light years, but I also am going to look at their spectra. And I want to notice, again, if there's this shifting of the spectral lines I described earlier, to tell me the velocity of the galaxy. Now, this shifting is showing a velocity towards us or away from us. Maybe you've heard of the Doppler shift. Many of you are familiar with that? It's a very subtle observational fact, but notice again in different objects how these same two lines that we'll pick are shifted slightly. If they're moving to the right, the object's moving away from us. If they're moving to the left, the object's moving towards us. So Hubble, again, painstakingly measured these little shifts and was able to come up with velocities of the galaxies. Here's his famous first plot. You can see there's quite a bit of scatter, but it's a good first plot, and later on it was improved. And the point I want you to see is the straight trend lines. The greater the distance, the greater the velocity. What does that mean to you and me? It means that the farther away the object was, the galaxy, the faster it was moving away from us. Can you visualize that? The farther away the object is, the faster away it's moving from us. Well, that told them the galaxies were flying apart. The universe was expanding. The universe was expanding. Does that put us at the middle? No, we've been there before, haven't we? Is humanity at the center of everything? No. Because if you put yourself in any other galaxy, you'd look back at our galaxy and see the same thing, wouldn't you? So it did not mean we were at the center of the universe. It just meant that all galaxies were moving apart. It was an expanding universe. Now you know why this astronomer became so famous, and they named the telescope after him, right? That straight line you see there became known as Hubble's law. Over the decades, it's been improved and refined. The error has been shrunken dramatically. This was perhaps, as I like to say, perhaps the most fundamental change in our view of the universe since Copernicus said that Earth wasn't the center. What do you think? I tend to think so. The universe is expanding. Well, if it's expanding, what else did that imply? See how science takes step after step after step? If it's expanding, getting larger, that means in the past it was smaller, wasn't it? And if you keep going back in time, what do you eventually get? Smaller, smaller, smaller. You're going to get to a very tiny universe, the beginning of the universe. So scientists quickly realized this discovery implied the universe had a beginning. It was not infinitely old. It wasn't eternal. That was a common idea at the time, that the universe always existed. There was no reason not to know until Hubble found this relationship that said there was a beginning to our universe. And of course, with his early measurements, he could make a rough estimate. Today, we've dramatically improved that. And we can now measure more precisely this expansion, and we can wind the clock backwards and tell you when the universe began. You probably know, some of you, the number. It's about 13.8 billion years ago. It's a pretty profound fact, isn't it? To know that there's a beginning to our universe. It wasn't always here. Somehow it began. Well, as we move through the 20th century, astronomers kind of developed the habit of always wanting bigger telescopes. because they became more powerful. There you see in the upper left the telescope Hubble used. It was put into place in 1917. He used it all through the 1920s, 1930s, and he really pushed it to its limit with the available photography of the day, 100-inch diameter. It took several decades to put together the next biggest telescope. You see in the lower left the 200-inch diameter Palomar telescope. Got to visit up there once and see that. That was the largest telescope in the world until about 1992, when you see the two in the lower right there, the twin Keck telescopes, twice the diameter, 400-inch or 10-meter mirrors. So our telescopes continued to grow larger. These enabled us to learn more, of course, about the universe, see ever farther out into space, measure things ever more accurately, more precisely, and improve our understanding of the universe that much more. But through much of the 20th century, there still was a dramatic limitation on our understanding, because most of that early work was done all in visible light. It really wasn't until the mid-20th century that we began to even think about other wavelengths of light. Look at the top diagram here. It's just illustrating how visible light can penetrate Earth's atmosphere. Radio light can penetrate Earth's atmosphere and reach the ground, but most of the other wavelengths do not. Now, that's not such a terrible thing, because that would be very bad for our health. High energy radiation striking the surface. Earth's atmosphere protects us from that. And again, that's not such a bad thing, but it does block all these wavelengths of light that astronomers would like to see. So what do? Well, as you can kind of guess here, you put your telescopes above the atmosphere. You put them on rockets, you launch them into space. Sure, you can still have radio telescopes on the ground, you can have those optical telescopes we saw, but maybe you've seen a few of these other ones that allow us to view other wavelengths, whether it's infrared, X-rays, gamma rays. And you probably know I need to update my slide here, don't I? We have a new infrared telescope, the James Webb Telescope now takes that place. Well, before we finish up, I just got to spend a minute on this particular change in our view of the universe. This has always been one of those profound questions that humanity's wondered about, really, for many centuries. Could there be other planets out there? How would you know? Clever astronomers came up with a couple of ways. Let's start over on the left there. Picture a star with a planet orbiting around it. Of course, we know the star's gravity is going to hold that planet in orbit, but don't forget that the planet has just far weaker gravity pulling on the star. And so in other words, as this planet is circling around the star is going to make a very slight motion like this. Now, astronomers knew it would be almost impossible to detect a motion like this, but they devised a way to detect a motion of the star like this, towards and away from Earth, if you're all sitting on Earth. Look at that spectrum in the lower left. If you look really closely, notice how as this planet is circling around the star and the star has a slight motion, notice those dark spectral lines shifting back and forth. That's that Doppler shift we talked about earlier. That tells us if an object's moving towards and away from us. In other words, the star has a very slight motion towards Earth and away from Earth, towards Earth and away from Earth. It's very small, but by the mid to late 20th century, we had the technology to detect it. How about in the middle? We have a second method. What if we happen to look at a star and the planet is orbiting around it with the plane of its orbit right in our view? In some small percentage of cases, the planet could move right in front of the star, and it could block a tiny bit of the star's light. Generally speaking, these are in the order of about 1% of the star's light. We might not be able to see the planet doing that, but notice what we do. We track the brightness of the light, and we see a dip there. Now, of course, it's crucially important that we see that dip continue to recur as the planet circles around the star. Okay, it should happen over and over again. How long would it take the planet to go around the star? Well, that's going to tell us the period of its orbit. How deep is that decrease? That's going to give us some indication of the diameter of the planet. All of this without ever seeing the planet. These are called transits. And you might think, well, it should be nice if we take a picture of one, and we can. But it's not easy. Because planets around other stars are extremely faint compared to the blazing light of the star. The star generally is somewhere in the range of about 1 billion times brighter than the planet. The star's giving off the light. The planet's only reflecting a little bit. So we've successfully used all 3 of these methods to detect planets around other stars. If you're interested in that, I've got another lecture on that on YouTube you can check out if you like. But this confirmed what we thought. We had learned a great deal about planet formation up to this time, and we thought, you know, it sure seems pretty likely that there should be other planets out there. And now we know of many thousands of them. So that has, again, broadened up whole new areas of research. What are they like? How big are they? How hot are they? How old are they? How young are they? It's a whole nother branch of astronomy that has opened studying extrasolar planets. I'm going to finish up with our last 2 dramatic discoveries. Have you heard this term, dark matter? Yeah, probably have. What was this about? Well, by the mid to late 20th century, a few astronomers were measuring the rotation of other galaxies, again, using the Doppler technique. And of course, in our own solar system, the planets orbiting the sun, they orbit slower the farther out they are from the sun. Why? Well, essentially because the sun's gravity weakens with distance. So we expected to find a graph like you see here in yellow in the upper left, where if we were to measure the rotation of a galaxy, the outer regions should be rotating slower than the inner regions. Seemed like a logical deduction, but look at what we did find in the green line. They were not slowing down. How could that be? Essentially, what that implied was there was far more mass in the galaxy than we expected or could see. Something invisible was exerting gravity, but we couldn't see it. So it became known as dark matter. It didn't give off light, essentially. Now we can simulate it, as you see in the lower right there, where it should be, what it should look like, but we can't see it. And I don't just mean invisible light, I mean any type of light. Dark matter does not give off any type of light. Now, here is one of these topics that a few of us were talking about before that we still don't fully understand. And sometimes people say, well, you know, what is it? We don't know. We're still working on that. I always tell my students we need some bright young students to help us out and join the battle, so to speak. But scientists are hard at work trying to figure out what it could be, what it could not be. Can we exclude many things? Yes. Can we narrow it down and say, well, it has to be kind of like this? That's where we're at now. But we still have not determined exactly what it is. But we're getting closer. We're getting closer. How about dark energy? Have you heard that term? This, I think, is even a little more bizarre. What's this all about? Well, this diagram is showing us possible expansion rates to the universe. Let me just walk you through it quickly. In red, if the universe only started 4 billion years ago, it would expand to a certain size, and it would literally slow down its expansion, and gravity would recollapse it. Well, the good news is it's not going to do that, so don't worry. But the other green and blue lines are coasting and critical, describe a universe where the expansion either is slowing down, but will never slow down to zero, or in blue, you see a nice steady line where the expansion is steady, okay? Look at the black dots that are our best measurements. Did they fit the first 3 lines? No, they don't. We have to actually create a new 4th line in yellow, and that tells us that early in the universe history, the expansion rate began to increase. So in other words, the universe is expanding faster than it used to be. And when you mathematically model that, you can see what it's going to do. It's going to just keep getting faster. So this was a dramatic change in our view of the universe, a recent discovery. Why is it doing that? We don't fully know. We have some pretty good ideas, and a lot of astronomers are working on this, but we still can't fully explain it. We can characterize it, we can describe it, but here's where much work is still going on. So, quite a survey, hasn't it been? You know this gentleman? I thought I'd finish up by letting Neil deGrasse Tyson share his thoughts on the most astounding fact about our universe. He was asked that, and I liked his answer, so let me go ahead and share that with you.
What is the most astounding fact you can share with us about the universe?
The most astounding fact
The most astounding fact.
is the knowledge that the atoms that comprise life on Earth, the atoms that make up the human body, are traceable to the crucibles that cooked light elements into heavy elements in their core under extreme temperatures and pressures. These stars, the high mass ones among them, went unstable in their later years. They collapsed and then exploded, scattering their enriched guts across the galaxy. Guts made of carbon, nitrogen, oxygen, and all the fundamental ingredients of life itself. These ingredients become part of gas clouds that condense, collapse, form the next generation of solar systems, stars with orbiting planets. And those planets now have the ingredients for life itself. So that when I look up at the night sky, and I know that, yes, we are part of this universe, we are in this universe, but perhaps more important than both of those facts is that the universe is in us. When I reflect on that fact, I look up. Many people feel small because they're small and the universe is big, but I feel big because my atoms came from those stars. There's a level of connectivity. That's really what you want in life. You want to feel connected. You want to feel relevant. You want to feel like you're a participant in the goings-on of activities and events around you. That's precisely what we are, just by being alive.
So what'd you think of his answer? By the way, that was sunset on Mars. Somebody can say you saw sunset on Mars. Food for thought, wouldn't you say? Food for thought. We have, in conclusion, learned so much about the universe. I tried to share some of our discoveries with you tonight. It's been quite a journey, but as we often say, we've really just begun. We've really just begun. We look back, and yes, we have come a long way in 400 years, but it's a big universe. And I think you can see how many times we've not only enlarged, but improved our view of the universe. And that was my point tonight, was help you to see that story, that adventure, I like to call it, of learning about our universe. That's why scientists are driven. That curiosity drives us to want to know, as I finish up here, what could lie ahead. So, give it some thought. Love to hear yours. If you enjoyed our presentation, I've got some other ones out on YouTube that you might enjoy. And I think I've mentioned to you before, there's also some short courses out on YouTube you can find if you'd like to go deeper in your understanding. So thank you very much for joining me tonight. And now comes your turn. I would be glad to take your questions. Let's see if there's things that you might like to either know a little bit more about or just want to comment on. So once you raise your hand, I can call on you, then we'll wait for a microphone to reach you, okay? Anyone have a question for me? Right here in the front center, sir. And then the rest of you want to maybe raise your hand too. They can bring another microphone to you as well, okay?
Something that I've always wondered about, how was it that the ancients could predict eclipses?
Good question. Anybody want to answer that one?
You.
It began with simply watching and noting when they occurred. Turned out they were periodic. We'd see one every so often in that location, that location, that location. It took quite a while for them to kind of put that together, but by simply just noting where they occurred and when they occurred, they began to slowly figure out the cycle of, oh, okay, so eclipses happen this often. We today know of something called the Saros cycle, if you want to look that up. Every 18 years, the sun, moon, and earth all align, but as I like to point out to my students, they align just pretty much the same, but there's this 8-hour difference. What do you think happens for those 8 hours? The earth turns a little bit. So if you saw an eclipse in one location, 18 years later, the earth turns just 8 hours, and the eclipse is now over here. So anyway, they notice things like that, okay? Is there one over here?
What do we know about black holes? And
Black holes.
do we know what they are at all?
I couldn't fit them in, sorry. Yeah, so the short answer is, first of all, I have a whole lecture on that, but black holes result from the very most massive stars. We described earlier that they are so massive that their cores are so hot, they burn through their fuel furiously, they explode as a supernova. But what remains to collapse is massive enough that as it collapses, nothing can stop the collapse. Gravity is so powerful, it crushes atoms. And mathematically, the math tells us that they basically collapse and contract down to size of 0. What does that mean to you and me? We can't hardly picture that. But these days we have solid observational confirmation of that. A black hole is where gravity has crushed the matter so much, no light can escape from it. Okay, so hope that helps. Is there one here? Oh, and then next hand over there.
First off, thank you so much for a wonderful presentation. That was really enjoyable.
Thanks.
We recently learned, detected some things about gravitational waves using pulsars, and that was really, really cool. Could you just give us a brief, like, Reader's Digest breakdown about what we did with pulsars to detect those waves?
I'm trying to think of the exact discovery, but on gravitational waves, Einstein's theory even predicted this, and everybody thought we'll never detect those, just quickly here, because they're so extraordinarily weak, and you could say tiny in the sense of their ability. But we did build the facilities to detect them here in just the last 10, 15 years. When a very massive object accelerates, whether it's orbiting, and when it finally crashes together, there will be this burst of energy that is emitted in waves of gravity. So pulsars are a great candidate for that, because pulsars are essentially what results from a very most massive stars that don't quite make it into the black hole category. When they collapse down to the smallest possible star that can still resist gravity. So they're extremely dense, and sometimes these objects are found in binary pairs orbiting each other, and the closer they get together, they are starting to emit these gravitational waves. Faster they move, stronger the gravitational waves begin. So pulsars are a beautiful laboratory for us to study gravitational waves. Was that kind of the question? Yeah? Okay, thanks. We can talk some more about that. I think we had a hand right here. Sure, go ahead.
Sorry, another black hole question.
That's okay.
So there was an astrophysicist that once made a comment, and I haven't bothered to look into it enough, and it's not my field, so I'm hoping maybe you can shed some light on it. as you mentioned, that when a black hole, it's when gravity becomes so incredibly dense that the black hole eventually reaches a singularity, a point of zero. And so the astrophysicist explained that anything that gets sucked into the black hole, rather than being spat out at an opposite end, literally just stays in the black hole for eternity. And that is, in a manner of speaking, on a particle level, the black hole, if you want to use poetic language, remembers every single thing that was ever sucked into it. So if you could reverse the black hole, you could literally get everything back out, and almost like, you know, remembering the DNA of everything that went into that. Is that actually how it works, or did I misunderstand? And if it is, how?
What happens in the black hole stays in the black hole, okay? That was well put, thank you. Let me try to talk back through that. So a number of things happen here, and again, I hate to make the pitch, but I do have a whole lecture on YouTube, you'll find. Something falling into a black hole, Einstein's theory of relativity tells us that as it begins to experience this stronger and stronger and stronger gravity, time slows down for it. Okay, so in other words, as it's approaching the black hole, it takes longer and longer and longer to reach it. Okay, so sooner or later, it's gonna reach this black hole, right? But once it crosses what's called the event horizon, where no light can no longer escape, no information is preserved. That's probably the best way I can say this. No information about what was that we don't know anymore. We can't know. Why can't we know? Isn't there some way we can? No, you can't look inside a black hole. No light's going to come out. So it's more than just, well, we can't look in it, but the information is destroyed. Think of it that way. Now, does the matter disappear from our universe? No, you can't do that either. Most of you know about conservation of energy and conservation of matter. It's not destroyed. A black hole, as it pulls matter in, is going to grow in mass. The mass is there, but we just lose the information about it. Look, some of you are familiar with the term entropy. You can look that up. It'll give you a little bit more insight on that as well. Over here, I think I see a hand. Way over there. Sure, go ahead.
Okay, I just wanted to know, how do astronomers know the difference between extrasolar planets and orbiting moons or other objects?
Okay, when you say orbiting moons around the extrasolar planets? Or
Around other planets. Like, how do they know the difference between, like, what is a planet and what is a moon orbiting around something?
Okay. At the simplest level, a planet orbits a star. Earth's a planet, Mars is a planet. Our moon orbits us. It's a moon. They can take greatly different sizes, compositions, different characteristics. So that's the distinction between a planet and a moon. Now, when you talk about an extrasolar planet orbiting a whole different star than ours, might they have moons? We suspect so. There's no reason they shouldn't, like in our solar system. We are just now at that point. I think we're about to actually be able to discover them and see them, but we strongly suspect they're there. Does that answer the question? Okay, thanks. And I see a hand somewhere back here. Yeah.
Thank you for walking us through these 400 years. My question is,
yeah.
what do you propose the next 400 years of our discoveries? How will that data be gathered? Will it be through AI and through algorithms and computer, or will it be through more observing tools like our telescopes and such?
That is an interesting question. Thank you, Beth. I think we're going to see probably a combination of both. There'll always be intelligent humans at the source of this. I don't claim to be an expert on AI, but it is already impressing us with some of its capabilities. Could that be powerfully and usefully put into employ? Yes, sir. I mean, some are already examining that. Because one of the things I do know about AI is it's very good at predicting things, predictive things that then smart humans can look at and say, oh, well, then let's go look at that, because the AI is telling us that's probably a good area for research. So, again, it remains to be seen how that's going to play out in detail. But boy, the next 400 years, boy, that's a tough one, There's so many unanswered questions. Many of you know there's some existing problems to still be resolved. I was talking with a few of you before we began, and we have a traditional method you saw Edwin Hubble employed to measure the rate of expansion of the universe. I said you wind that number backwards, you get an age for the universe. This is that number. Well, just in the last, maybe 20 years or so, we developed an alternative method. And at first, the two methods, their errors kind of overlapped. In other words, both seemed plausible, and they both had a moderate agreement. But as we improved each method, the error that we measure would shrink, and the two began to diverge like this. So now we have something that has been called the Great Tension. There's the traditional method gives us this number for the age of the universe, and the new method gives us a different one, and they both look pretty solid. So that's a big question. Okay, now that's a question we already know about, right? So there's, a lot of you know, there's the known unknowns, and then there's the unknown unknowns. What questions will we ask 50 years from now, 100 years from now? It is a fascinating thing. I've often tossed it in my mind. I don't get very far on it because, you think about the people, let's call it 200 years ago. If I could talk to William Herschel, he didn't even know about photography. He didn't know about spectroscopy. He didn't know about all those things. And if I were to say, we can tell you how massive that star is and what it's made out of, and he'd be like, how could you possibly do that? Same thing with us. We have learned our lesson, but boy, it's hard to project into the future, So thanks for your question. Can't give you a solid answer yet, but I will stay tuned because astronomers are always working. Another hand over here.
So how does relativity sort of affect like the past of astronomy when it's developed in the early 20th century and the future of astronomy? So like, do astrophysicists have to redo past calculations, and how does relativity help them discover new things past its development?
So relativity, okay. Boy, if there was anything that changed our view of the universe, it was relativity. I like to say that, by the mid to late 19th century, astronomers got just a tiny bit smug that, we've kind of got a lot of things figured out. We kind of understand using Newton's laws, how things move and act and all that. And then this relatively unknown young man, Albert Einstein, raised his head and said, I got another idea. Boy, what a change that has brought for any of you that are familiar with it. Again, another lecture there. But how has it changed? Can you repeat that last part? I wanted to just make sure I got it clear. Sorry.
So like, how did like astronomers have to like redo past so like their parallax calculations and their luminosity calculations?
Yeah. Many of the calculations are done in a realm where relativity is not significant. You drive your car down the highway, relativity doesn't apply. You're going 60 miles an hour. Even you fly a spaceship at 25,000 miles an hour, relativity barely even has any effect. But relativity only comes into play in more extreme environments. And so one of the reasons my students study it is because they are extreme environments out in space. We do find objects moving at very high velocity, and we must use that theory to get a correct answer and a correct understanding. Other times it's very strong gravity. Einstein's theory was the very first, believe it or not, to predict gravitational waves. And it took us 100 years to detect them. So it's essential for astronomy. It's not so much essential for everyday life, but it has changed the way not only astronomy views the world, of course, but in everyday life, other realms of physics require relativity to explain. And so it is a much more solid, much more comprehensive theory of the universe that allows us to explain black holes, explain gravitational waves, supernova, reactions, those kind of things. You must use that theory. Newton's theory is different ways to say it. Limited, incomplete. Does that kind of answer the question? Okay, thank you. And any others? I'm sorry, I can barely see one over there. Sure.
So how are the colors picked for the images from the James Webb Space Telescope?
Very good. For the James Webb Space Telescope, it's images, previous lecture. It's taking infrared light, isn't it? Can we see infrared light? Not really. So at some point, they have to pick. And basically what they do, simply put, is they'll say, well, look, the very shorter infrared wavelengths, let's represent those with blue. and the longer infrared wavelengths, let's represent those with red. Basically, we're assigning, you could call it a false color to it. It's not technically red, but our eyes need to see something. So that's how they kind of go about that. And they say, this is what it would look like if you could see infrared light. Okay, does that help? Back there?
So if we can't see what dark matter is, we can't see what is inside a black hole, do you think that if and when we get better at studying what's inside a black hole, that might help us better understand dark matter? Or if we better understand dark matter, might that help us understand black holes more?
Anything's possible, but let me try it. As you were saying that, I had a couple ideas. I want to make sure I put these together in a good way. So these are two distinct objects. When we first discovered dark matter, there was a lot of options, a lot of possibilities it could have been. People said, well, maybe there's trillions of planets floating out there and they're all adding up to be dark matter. No, we've pretty much ruled that out because we think of ways, well, if there are, how could we find them? Well, we would find them in infrared light and we don't see them. Okay, so we eliminate that, and then we eliminate that, and we eliminate that. We narrowed down dark matter. There came a point where we began to say, dark matter is almost certainly not large, massive objects. It is almost certainly some tiny little particle. We've pretty much constrained it to that, okay? A black hole is a large, massive, macroscopic object. So the properties kind of don't match. Do black holes contribute something to dark matter? That sounds like a pretty good fit, but here's the catch. Black holes come from the most massive stars when they blow up. There's very few of those, relatively speaking. So there's a relatively very small number of black holes in the universe. They don't add up for dark matter. Again, astronomers and physicists have constrained dark matter down. It's almost certainly got to be some particle. They have different ways they describe they call it the particle space. Is it this property, this property, this? It's right in this area right here. And that's one of the big things, is that we've devised experiments to constrain so much, we're getting to the point, several teams have said, look, we're going to know in the next 5 to 10 years. And I hate to say we've heard that before, but they're like, it has to be in this space, and we're going to pinpoint that, and we're going to know. And if it's not, then we got to do one of these. We got to step back. Okay, let's all think about this again. So time will tell. That's a very interesting discovery waiting to be made. Is that a question, or is that a... All right, any others? These are good questions. Boy, you guys are making me earn my pay tonight. There's one down front here, I know. Can we get a microphone? Oh, over here, sir. Please, go ahead.
I just had a question. I think it was in a newspaper article I looked at, but observations from the James Webb Telescope are causing some to call into question the Big Bang Theory.
I've seen some headlines, and I have kind of read through some of the news stories, and I get an understanding where they're coming from. They're open questions. I haven't taken the time to go into great detail and really evaluate them. I must be honest with that, but that's something, again, some people feel negatively about. Well, I thought we knew all this, and what? But many astronomers go, wow, a new mystery to go look at. So time will tell. I haven't yet really, investigated and evaluated them enough. I will say this, that whenever a discovery is made like that, or let me back up. Let me be careful with my terminology here. Whenever a new observation is made, we bring down some new data, it's real easy to jump to some conclusion. Oh, well, this must mean that. Hold on. There's a lot of work to be done, as my students will tell you, between observation to understanding, okay? So while I'm always, and I think most scientists are always open to these new observations, that's what we do, that's what we live for, there's a long path before you get to truly understanding something and establishing it as accepted. So that's what I would encourage you to do. It's an exciting time with James Webb observations coming down. Many unexpected things. We think that's great. But remember, give it some time to be evaluated before we get to that stage where we start to say we think we've really found something new. We almost hope we find some, new things, but that takes a lot of work to get to that point, Okay, so I'll just kind of leave it with that one. Was there one more I thought I saw? Yeah, please go ahead.
Hi. First, thank you for your presentation. It was wonderful. I have kind of an odd question. Do we know what gravity is? And by that I mean, so I'm holding my car keys, and and there's the Earth.
What is that?
And there doesn't seem to be anything attaching my car keys to the Earth yet. When I let them go, somehow the Earth says to the keys, "Come here," and they do.
Yeah, that's a good question. I like that.
What is that? What if there's nothing connecting them? Why do my keys listen to the Earth?
Why do they go there? Yeah, it's a good question. It really is, and that's one of those simple, fundamental things that scientists not only asked in the past, but we continue to do today. So just briefly, the first real good understanding, I mean, you can go all the way back to the ancient Greeks and their ideas, and they tried. Isaac Newton, we talked about this law of gravity. Oh, two bodies attract each other, and they attract it like this. But that's not your question. Your question is, why do they attract each other, right? And Newton actually, I believe, owned up to that. He said, I don't know what it is. My equation describes what it does. And that's true. So you're agreeing with me. So now along comes Albert Einstein. He says, this whole thing with this mysterious force, that nobody knows what this magical force is. He's like, we have to think about it as a force. Some of you heard this. Let's envision that matter, let's pick a planet out in space, curves space. What do you mean by curved space? Picture this floor appears nice and flat and straight. You can draw straight lines. You can measure 90-degree triangles and blah, 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 all that geometry, right? But if you somehow were magically able to take this and kind of curve it, objects on the curve would move a little differently, wouldn't they? So Einstein's idea was, now you got to think three-dimensionally, but space is curved by matter, and he proved this. Some of you know that his famous experiment in 1919 was he said, when there's a solar eclipse and the sun is blackened out, a star's light right near the sun is going to be shifted because it's going to pass through curved space. And everybody's like, what? And when it happened, the world was astonished. This is what made him the rock star of his age, because he was right. The light that we all know travels in straight lines curved. Why did it curve? Because the space itself was curved. Now, you're saying, okay, so matter curves space. That's what gravity is? I don't think we can still say what it is, but we can say that that's a better explanation than some mysterious force. And so we have a better understanding of it. As far as what it is, you're like, well, what curves the space, right? That's the next level of the question. We can't answer that yet. Some have suggested and even postulated maybe there's some mysterious particle called a graviton that we haven't been able to put our finger on yet, and maybe. There are different theoretical approaches to it to be able to say, well, this might work, or that might work, or that might work. So we are always improving, but do we have some definitive answer, like what it is? Not really. Sorry. Any final ones? There's another one over here. You guys have good questions. And we got a couple over here. Okay. If anyone needs to leave, we understand that, but I think you'd probably like to get your questions out, huh? Go ahead.
Hi. On the Milky Way slide,
okay.
You had a call out for class O and B stars.
Okay, way back here somewhere.
Outside of the center, and I'm wondering, on the right-hand side there, and I'm wondering if that's intended to represent an anisotropic distribution of those stars. I mean, are they all on the outside of the galaxy? And if so, what does that say about the distribution of heavy elements that would be produced by massive and hot stars?
It's a pretty good question, actually. At first you might think, well, there's just a yes or no answer, but what you're getting at there, I know, is, first of all, you said, so the O and B stars, it's an anisotropic. Are they only out there? Roughly speaking. The Milky Way has two major components. You can kind of see here a large central yellow region. We call that the galactic bulge there. The reason it's yellow, because those are lower mass stars. They're not quite as hot, and they tend to give off yellow light. They also tend to live a long time. They're very ancient stars. You see this beautiful disk out here. The artist has shown it more in other colors like pinkish and bluish. The disk is where star formation has continued, and therefore, on average, the stars are younger. They tend to be more massive. Since they don't live as long, they can be younger. That's what O and B stars are. They're very massive stars. They're very hot. So they're trying to illustrate here that the O and B stars are out in that bluer region out there. That means, well, they're very hot, they're very young, they're very massive. That's what they are. Was there a second part to the question?
Are they, does that mean that there's more heavy elements?
Yes. Good question.
Sorry.
Yeah. Are there more heavy elements out in the disk? Yes. In other words, that, again, central yellowish bulge, these are old, low-mass stars. They've not made nearly as much heavy elements through all of their years of fusing energy and all that. They're kind of relics from early in the galaxy's history, okay? But in the disk, several generations of stars have already lived and died. And every time a generation lives, it creates a certain amount of heavy elements. Some of those massive stars, those O and Bs, they blow up and they spew that stuff out into space. Well, that stuff eventually makes the next generation of stars. They're already enriched in heavy elements. Some of those, some percentage of those, are going to be massive O and B stars. They make more heavy elements. They blow up and spew it out into space. So his point is, the disk is enriched in heavier elements than that central region. That's all great. Why are you and me interested in that? In that central region, there's not very much heavy elements to make planets. But out in the disk, there are. And that's why, that's where we live. Our star inherited several generations of heavy elements from previous generations. It was able to form planets. Here you and I are. We're made out of carbon and oxygen and iron and all that. So you start to see a little bit of the kind of history of the Milky Way here and how our planet got here. Will we find very many planets in that central bulge? Probably not very many, maybe a few. Those are old stars with very little heavy elements. They're mostly hydrogen and helium. You don't really make planets out of that. So good question, thank you. That helps maybe add a little depth to this one. Okay, let's go to this question here.
Yeah, regarding the expansion of the universe, galaxies are moving away from each other, okay, in a three-dimensional thing. My question is, how is it, if that's true, how is it that the Milky Way and Andromeda are on a collision course?
Ooh, good question. Did you guys know that? Does that worry you, that we're on a, you know? Yeah, so we have precisely measured the motions of the Andromeda galaxy relative to us, and yeah, we're going to end up doing this. The good news is we got several billion years. Okay, the short answer is, yeah, but I thought you said the whole universe is expanding, right? The whole universe is expanding, but the Milky Way and Andromeda are close enough together that their gravity is strong enough to overcome that expansion. The expansion really kicks in over larger distances. There's not any one single number, but our whole, we call it the local neighborhood, we have a number of galaxies that are all kind of, we call it gravitationally bound. Our gravity's strong enough to kind of hold us in a group. We can look out and see other groups doing the same thing. These galaxies are holding each other together in a group, but you can almost think of it like, well, the groups then are flying apart. That might be a simple way to, okay? Is there another one over here? Sure, go ahead.
So kind of along the sequence of improvements that you've given us through your presentation, you know, there were like wild card people like Ptolemy, Copernicus, Galileo, Einstein. Who's like a present day rogue? Who should we be keeping our eye on?
Place the long bet, huh?
You know,
Yeah.
What's, yeah. That's why we're here. Yeah.
That's an interesting question. I heard it put that way, but so first of all, it's true. There is sort of the, what do I want to call it? Just the typical way science progresses gradually. But once in a while, somebody stands up and goes, "I got this whole new idea," right? Tell me, Einstein. Who is this guy? He published it in this journal nobody read. He published his first theory in 1905. You remember we talked a little bit about dark matter and dark energy. And what in the world, how come we can't still explain this? We've known about dark matter now for like 30 years, A few people have stood up and said, I got an idea. What about this? And you go, what, really? Some have said, what if gravity is not always a constant? Now, mind you, what I mean by that is it's not going to change in this room. It's not going to change on our planet. It's not even going to change in our solar system. But what if over huge, huge distances, millions of light years, gravity has maybe a little change in its strength? And you can work that backwards and say, oh, well, then I can just go ahead and change the numbers, fudge the numbers to the point where I can make this all work and explain dark matter. A few people said there's no magical dark matter out there. Gravity works differently than we think. I'm not saying to bet on that because the astronomical community, we've heard this now for almost 15, 20 years. We said, okay, let's just go test that. Tell us more. Tell us about it. And a lot of smart people raise their hand and say, if that was happening, then we'd see this, or we'd see that, or we might see this over here. Let's go test these things. And every time we test one of those, we're like, sorry, dude, didn't work. So people stand up with some unusual, innovative ideas. You got to give them their chance. You got to give them their hour on the stage, and you got to say, all right, convince us. And believe me, scientists are real good at shooting arrows at each other's ideas. Yeah, but what about this? You'd see that. You got to go test this and check that and come back and write another paper and blah, blah, blah. So on and on it goes. It's usually, almost always, a very kind of friendly thing. Once in a while, it can get a little heated up a little bit like, So is there any right now that I would point to say, watch that idea? Nothing really comes to mind. Like somebody's got this really great idea, Nothing comes to mind, but people have thrown out some interesting ideas, About 7 years ago, measurements were made. I was telling somebody, I think, before the lecture. Einstein said the speed of light is one of the great constants in the universe. You probably heard that. And everything else can change, but you can't violate the speed of light. It's rock solid. It's just, Well, over the decades, there have been many, many tests done to challenge that. And I do mean challenge. And every time they failed. I want to say it was 2014 or 2016, a team came out and they said, okay, we got these results and we know what you're all going to say, but we think we found an exception to something moving faster than light. Now, how do you think the community responded? Okay, tell us about it, Of course, your initial reaction is, we've done this before, but no, that's okay. We keep challenging our theories. We keep testing them. That's okay. So they tested them. What you do in that case is you say, we're going to appoint independent teams to, first of all, reproduce your results. Can we do that too and come up with that result? And if so, what might explain that? And the original team was very good about it. They said, we know, we get it. That's the process, so go to it. And it took about 1.5 years, and finally they came back and they said, we found it. We found why you got that result. Believe it or not, it was an equipment problem. And you might think, come on, really? It's like, no, but this is extraordinarily delicate, complex to the extreme stuff, and it took a long while to track that down, say, I forget what it was, something about the sample you used for your atomic clocks was blah, blah, blah. It's like, wow. So no one thought less of that original team for throwing that out there, but the original team did the right thing as well. They said, thank you very much. We accept that. We get it. That's why it seemed the wrong way. So, again, I keep saying that's how science works, is sooner or later the community works together. It might take a while to get to the real answer. Anything else? There's still a few more out there. My goodness, go ahead.
Hi, it's me again.
Hi, me.
Okay, so according to the second law of thermodynamics, and you mentioned earlier entropy, the universe is going from a state of perfect order at the start of the Big Bang gradually to disorder, and according to the laws of physics, mathematics, and chemistry, in tens of billions of years, the cosmos will end in the inevitable heat death of the universe. So very, very lovely thought.
Depressing, yeah.
But the question is that an inevitability, or are there other scientific hypotheses or theorems that could posit alternative fates for our universe?
That one seems to be a pretty hard and fast rule as I understand it, but the catch here, and I don't want to reassure you all, in other words, order throughout the universe will gradually diminish, right? And the catch is, that doesn't mean pockets of order can't remain. That's the key. You can maintain or even build complexity if you take the expense from somewhere else. And that's a very general statement, I know, but I know what I'm talking about. So that's why we're here. The Earth has extraordinarily great order. Why didn't it all just decay into nothingness? Because it's preserved here for whatever the multitude of reasons are. The Earth is extraordinarily complex, but out in space, there's vast clouds of matter with no complexity to kind of make up for it. So not too worried about it. But interesting question. Interesting question. So any final ones? There's still a few more? Okay, sure. Go ahead.
So this might kind of tie in with that answer there, but earlier in your presentation you said that all stars get old and die, and so to pick a star, the North Star eventually would get old and die, but maybe not, according to what you just said.
But maybe not?
Yeah, maybe it won't.
No, all stars will get old and die.
Even the North Star, then?
Yeah, in other words, the North Star's a constant, right? No, I guess let me clarify a little bit, is any natural, object like a star is going to eventually lose its order. Stars are made of, gas. In their cores, they're hot enough to make energy. They use up the available gas to make energy. They can't make energy. They change. They either blow up or they go through this stage or that. And there's an end result that is going to slowly lose its heat. We would consider that similar to saying, well, it's losing order, so to speak. It's losing. So a natural object like that is not really what I refer to there. What I refer to is somehow you'd have to develop that order at the expense of that. Does that make sense to say it that way? I'm not sure if I'm wording that well. But those natural systems, a star in particular, doesn't have the ability to increase its complexity. It's going to follow the laws of physics. It's going to use up its energy. It's going to gradually cool down. So the star is maybe not the right example. If you're looking for a natural system that would build complexity, again, here our Earth is a beautiful example of that. How did all this complexity come about? That's another question. Okay, any other ones? Whew, you guys really had some good ones there. So thanks again for coming tonight.